Okay.
So, do you see it?
I see, yes.
Okay. Okay, yes, here it is, yes. So please, then
yes, let me say a few words. As far as I know, Borja is a PhD student of Thomas Schiller in Vienna, and I met Borja last year, and it turned out that Borja is also interested in cyclic and non-wellfounded proof theory, just like me. So I like that today we have a talk of Borja about his approach to this subject based on coalgebra recursion. So please.
Thank you, Daniel. So yes, I'm a PhD student at the University of Bern under the supervision of Thomas Studer. And this work I'm going to present is joint work with him and also with Lucas Zenger. And as Daniel said, this is an approach for doing cut elimination in particular, but more generally, any kind of transformation of proofs in the non-well-founded setting. And to be more specific, is not in any non-well-founded proof, but is, let's say, in the simplest case of non-well-founded proofs. That's the reason you can propose such a method so uniform. And the main tool we are going to use is Coalgebra, as this is said. So basically, we are going to use Coalgebra to define a co-recursive process, but we will enter into those details later. To start, although this is a uniform method, let me introduce a logic so we can have a reference of everything that we are doing. So we are going to be working with Gregorczyk logic, which is a modal logic, as you probably know. We are going to work in this restricted language. Obviously, we also have variables. This is not a real restriction because the rest of connectives can be defined as usual. And here I have written the syntactic description of the logic. So basically, it's the smallest normal modal logic with this axiom here, which is called Gregorczyk axiom. And here there is also the semantic description, which is not going to be so interesting for us, but maybe it's good to know that the frames, the Kripke frames that describe this logic are chain converging. And with this, I mean that whenever you have an ascending chain of words, it must be one point when it stabilizes. So from one point, it should be the same word over and over again. This is important for soundness of the proof of the sequence calculate that we are going to see. And maybe it's good if we try to do the soundness proof a little bit quick because it can give you an intuition of why the proof system is as it is. Because otherwise, there are some features that at first sight may look a little weird. And here below, we can see some important properties that Gregorczyk logic has. But for us, the important property that is important for this talk also is this one here. So basically, Gregorczyk logic has a simple non-well-founded sequence calculus. And this calculus was proposed already by Yuri Sabativ and Daniel Shankanov. And this is the calculus we are going to use. As I said, this is everything for having a concrete example of the method. So the method in general can do proof translation, so functions from proof to proofs in non-well-founded system. And in a particular concrete example, we can show cut elimination for the non-well-founded system of Gregorczyk logic. Now, in order to any of this make sense, we have to explain what is a non-well-founded sequence calculus and also what is a simple non-well-founded sequence calculus. So this is, well, first of all, sequence I assume everybody here knows sequence, but just to fix some conventions that may vary from text to text. And here, a sequence is a pair of multisets, finite multisets of formulas. And as you probably know, this pair can also be denoted like this. And the interpretation of this as a formula is taking the conjunction of the first multiset and the disjunction of the second multiset and making an implication. So we can call this as the antecedent and this as the consequent. And now we can define the union of sequence, just making the union component-wise. As I said, these are multisets, so this is multiset union, so taking into account repetitions. And this is some notation I'm going to use, which I believe is not that standard, so maybe it deserves some explanation. Basically, whenever you have a sequence and a finite multiset, if you put a black dot on top of the finite multiset, you can consider that you are adding those formulas to the antecedent. And if you put to the antecedent, as you can see here, and if you put a white dot, then you are adding them to the consequent. So in some words, if S is something of shape, if S is equal to some pi arrow delta, then, well, this one will be pi gamma delta, and this one will be pi arrow delta gamma. And we have the same convention, but also for formulas instead of finite multisets. So yeah, what you have to keep in mind is that black means left and white means right. And this is just for writing some things shorter, but this is obviously not important, it's just a notation. Okay, now that we have fixed the concept of sequent, we can define what is a non-well-founded proof system, and in particular, a local progress non-well-founded proof system. So the simple here means local progress. So in general, we have that in a sequent calculus, there are rules, and rules are just collections of sequent rule instances. Now, a sequent rule instance is just a pair of some sequence which are the premises and a sequence that is the conclusion, no? And we write rules with this long double arrow, and you will usually, if the premises are this, and C is the sequence of the conclusion, we will usually write this as this. So with that, we obtain a proof system. Now, the non-well-founded is not really into the system, but in what you call a proof. For us, let us fix the concept of pre-proof, which is here. And basically, a pre-proof in a system is a non-well-founded tree generated by the rules. If I say non-well-founded tree, everybody follows, right?
I follow.
Yeah, I forgot to say this, but it would be good if we have some interactions, because there are many technicalities to the method, so it can be hard to get what is happening. So I want you to interrupt me if you don't understand anything, and yeah, we can have a conversation during the presentation. I believe it's important. But yeah, well, so basically the non-well-founded comes from allowing non-well-founded trees, and it must be generated by the rules as usual. And the local progress comes from having an additional function, which is this function here, which basically whenever you give this function a rule and a rule instance, you will obtain a subset of 0 to n-1, where n is the number of premises. The idea of this is that whenever you have a rule instance, of a particular rule, So we put the rule explicitly, just in case one rule instance can be an instance of more than one rule. So we put the rule explicitly, just in case. And basically what this function is saying, some premises here, so maybe these ones, are progressing in this rule instance. What we are going to say that there is progress when you go from the conclusion to a progressing premise. Here there are more drawings, so this can be easily understood. So here we have a non-well-founded tree. Non-well-founded, yeah.
Sorry for interrupting. Just in case, could you give an example where an instance is an instance of several rules?
So yeah. In this particular case, it doesn't happen in the proof system that we are going to use of Gregorczyk. But I remember, well, if you have, yeah, I don't have any specific one in mind. I know that at some point I have encountered one, and that's the reason to explicitly put the rule, but it is true that it's not the most common thing.
Okay.
But just in case, I prefer to put the rules, just in case. But yeah, right now, I don't have any particular example in mind.
Maybe in the context of the modal calculus, or
yeah. In some modal calculus, I believe it can happen because some modal rules do a lot of things at the same time, and maybe some of them may collide. Or maybe if you put if one side of the sequence is empty or something like that, it may happen that two are the same. I believe it just can happen. So just to be safe, I want to say that, because what we want to consider is that some rules because usually rules are schematic, we don't, in fact, usually a rule is not any collection, it's a schematic collection. And we want to say that in some rules, some premises are progressing. That could be another formulation of this, just for easiness, I didn't want to treat rules as a schematic and just as collections.
I see, just for more safety, so to say.
Yeah, it's just to be safe, to be sure, because in principle, nothing tells you that this cannot happen. And I'm pretty sure sometime in my life I found such a system, but I don't have it in mind. Well, in any case, so we annotate the rules just for safety. And here you can see an example of part of a non-well-founded tree and how we treat them. So basically we have the vertices. Now to each vertex, we have a sequence and a rule. And basically what we impose is that if you take the sequence, the rule, and the premises, this rule instance must be a rule instance of this rule. So that's the condition for being a pre-proof. The other condition that is needed for being a proof is basically this one here. So whenever you have an infinite branch from the root, it must be the case that there are infinitely many positions in this branch, such that when you go from the conclusion to the premise, you must progress. And again, this progress is defined. So for example, here in this particular example, if our system has this L function, which is saying basically at rule R0, at this rule instance, maybe I forgot to explain this. This one here means the right premise. And this is because for us, trees are going to be collections of strings of natural numbers. So basically you can think about this node as the empty string. Now this is the string containing 0. This is the string containing 1. Then this is the string containing 1 and then 0, and so on. And so basically this one is the number of the premise. So this will be the 0 premise, and this is the 1 premise. So the progress occurs when you go from here to here, but not when you go from here to here, because otherwise we will need a 0 in this set. So that's the whole idea. It may seem as a technical definition because this function maybe doesn't look so nice, but the idea is pretty simple. It's basically at some premises of some rule instance of some rules, you make progress, and at the others you don't. And whenever you have an infinite branch, you want to go through progress infinitely often. And we call this local progress, by the way, because in order to know if you progress from one vertex to other, you only need to have the rule instance and the rule you're applying, but you don't need to look to the whole branch. In other non-well-founded systems, for example, in trace-based systems, in order to know if something is progressing, you need to look at the whole branch, and that complicates things. We are not going to treat that case here, sorry. But yeah. Okay, now for a concrete example of such a system, here we have the non-well-founded system for Gregorczyk. So as you can see, the 4 rules here are pretty standard. Now here we have a rule which expresses reflexivity. Remember, the black dot means that is on the left side of the sequence. And here we have the box rule. Now, this is the point where I believe that someone new to non-well-founded proof theory will find this rule a little bit strange. Because if you think about it, this sequence is a weakening of this sequence. So for sure, if you have a proof of this, you should have a proof of this because it's just a weakening. But this is not how it works, because this rule, in fact, has some additional asymmetry, which is this one. Basically, you only make progress in this system when you go from here to here. But you don't make progress if you go from here to here. So this asymmetry doesn't allow you to think about this in that way. And if you want to reason why these rules make sense, you can try to show the soundness of this system. And basically, you can show that for any model on this wall, this sequence is forced. Also this one. Now, for any model and any wall that forces these two sequences, the bottom one is, sorry, is also forced. Now, for any model and wall that forces the top sequence, here it happens the same, and here it happens the same. So this is in some sense the soundness of any of these rules, but for this rule, it is a little bit more special. What you do is assume this sequence holds in W, and this sequence must hold in V, where V is basically a successor of W, distinct from W. And then you can show that the conclusion holds in W. Once you have established this soundness of these rules in this way, what you can do is the following, because notice that, well, soundness is going from a proof to the validity of a sequence, no? Usually this is done by induction in the height of the proof, in the finite proof theory case. However, here we have non-well-founded proof, so there is no height to induct on. So you do an argument by contradiction. You assume that the sequence is not valid and obtain a counter model. A counter model will be a model and a wall where the sequence doesn't hold. Now, if you look at the rules, you can construct a branch that starts going up, and in any of these rules, while you go up, you will stay at the same wall. You will never reach these cases because then the branch will end in something that you know that is not a counter model. So the branch must continue infinitely often. Now, what you know is that in any infinite branch, you must go from here to here infinitely often. And this means that you are going from a wall to a successor strictly distinct from the wall infinitely often. what is happening is that you are creating a chain that is not converging, and then you are obtaining an absurdum. Because if you remember, the frames that define the semantics of these logics were chain converging. So that's the reason of, well, at least that's how I understand this rule. Basically, if you go to the left, you are staying in the wall. If you go to the right, you are going to a distinct successor. Okay, so I think that gave a good intuition of the system. And here there is an example of a proof. So you can see here that, well, basically you have an infinite path if you go in this way. Because the idea is that in these 3 dots, you should imagine that we put this fragment again here. And then you will have 3 dots on top here. And you will put again this same on top, and so on and so on. And then you will obtain an infinite proof. This is an infinite proof and not only a pre-proof, so it fulfills the branch condition. Because if you notice, in order to go to the 3 dots, you go through the right premise of a box rule 2 times. By the way, I forgot to mention, this is just a proof of Gregorczyk axiom. If you look at this system, and you take finite proofs, you won't have Gregorczyk logic. But once you allow these non-well-founded proofs, and with this branch condition that ensure that the system is sound, then you get Gregorczyk logic. As you can see here, you can prove Gregorczyk axiom. By the way, I'm really sorry if I'm pronouncing Gregorczyk, but I'm not so sure if it's the correct pronunciation.
I don't know. Valentin Borisovich, do you know how to properly pronounce Gregorczyk?
Да-да, вопрос какой-то?
Do you know maybe how to pronounce the name Gregorczyk properly?
Grzegorczyk.
Gregorczyk.
Okay.
Grzegorczyk, yes.
Okay, I will try to pronounce it with
Grzegorczyk?
Чик.
Is it an original pronunciation? Yes, Grzegorczyk or
Grzegorczyk.
Grzegorczyk.
Polish, it's difficult to learn this. It's a specific sound.
Okay, for now on, I will say GRZ. So I'm not mispronouncing anything. GRZ,
Yes.
GRC logic.
Yes.
Yeah. Okay. So let me continue. So basically now we are going to explain why this local progress is so, the essence of why local progress is the easiest case to treat. Basically, the idea is that in any local progress system, you can see a proof instead of seeing it as a non-well-founded tree. You can see it as a finite tree which has attached some finite trees on top, which has attached with, and those finite trees may have attached again some finite trees and some finite trees and so on and so on. This is what is going to facilitate the treatment of these proofs. And the idea of how to do this is as follows. Basically, you define an equivalence relation for any, oops, that's the incorrect tool. So here, for giving a proof in a local progress system, you can define an equivalence relation. And basically, this equivalence relation says that 2 walls are related if and only if, when you go from one of them to the other through the smallest path, you do not go through any instance of progress. And by this, I mean, notice that it may be the case that you need to go contrary to the direction of the edge. But for example, if you go from here to here, since this is an instance of progress, we also count going from here to here as passing through progress. So basically, you relate nodes such that you can go from one to the other without progressing. Then what will happen once you have that binary relation, it's going to be an equivalence relation. So it will give a partition. And basically you will have that any element of the partition will have these properties. And basically, if you look at these properties, what they are saying is something really simple. Any element of the partition can be seen as a finite tree. It must be finite, it must have a root, and it must be convex. So you cannot have things like so imagine the circles of one particular column of one particular color being elements of the same partition. So this cannot happen because if this one belongs to the blue partition, this one belongs to also to the blue partition, but you have a middle node that doesn't belong to the blue partition. So if you fulfill these three properties, what you can see is that any partition is its own finite tree. So we can have this picture of the non-well-founded tree. So basically, we are interested into a study in general trees with an equivalence relation or partition that fulfills this property, which we call some notation. We call these properties the fragmentation properties, and any member of the equivalence class is called just a fragment, a finite fragment. And we call these trees. So a tree with this partition, this kind of partition, is called a finite fragmented tree. This finite meaning not that the number of fragments is finite, but the fragments are finite themselves. Are any questions about this?
Borja,
Yes.
instead the second and the third condition, we can say that just that fragments of classes are connected sets in the tree.
What do you mean? Well, that they are connected is the complexity?
There is a path connected. It means
Yeah.
that between any two nodes in one fragment, there is a path. There is a path entirely.
Yeah. I think that condition and being finite should be equivalent, and that's also the reason why this particular equivalence relation, which is defined using that, fulfills the properties. But
Maybe a little bit shorter. Just say that this is a partition on a connected finite component.
Yeah, you can change these two conditions. Oh, it's not working. Well, basically, you can change condition 2 and condition 3 for being connected. Yeah, maybe actually, it may be a nice change. We will see because the proofs are really, how do you say? So I'm going to explain that now. But the proofs are really technical, so I'm scared of changing something a little bit and making them more complex. That's also, but we will explain that in a second.
It's interesting whether you apply these conditions to the third and the second one, maybe simultaneously, or somehow you rely on them in different places.
Yeah, I'm not so sure right now, because basically in this work there are two kinds of proofs. So there are the proofs where will allow us to define the method. So these are coalgebraic proofs, and these are really complex because, okay, in general, and basically you have an end of functor over the category of sets, and you want to show that it has a final coalgebra. It has coalgebras, you want to show that it is final. In this particular case, it is particularly easy because there is an abstract coalgebra theorem which guarantees that by the properties of the end of functor, you will have a final coalgebra. However, the problem is that you don't know how this coalgebra is exactly. And since our purposes is doing proof translations, and usually proofs are non-well-founded trees, we want to have an easy way of going from the non-well-founded tree to the extractor of the final coalgebra and back. That's the reason, and this complicates, or they are not more complex, but suddenly you have to prove a lot of technical things in coalgebra because you want to guarantee that this particular representation is a final coalgebra. And that's why you get a lot of technical proofs. That's the only reason. Either you get technical proofs to show that this particular representation is a final coalgebra, or you get that technical proofs to show that you can go from non-well-founded proofs to the final coalgebra and back, which in fact are equivalent, no? Because that will be an ISO. And then that's the reason I'm scared of touching the conditions, but maybe it gives simpler proofs. We will need to check it. Putting connected.
It seems that your text with Lucas and Thomas, in any case, is shorter than of my and Yuri's about logic. So I see that there are surely some small technical details that should be checked in order to apply this co-recursion algebra accurately. But it seems that in any case, your language is more is shorter, more.
No, yeah. So the point is, you have to do these technical details, but you have to do it once. And when you have to do it once, it's really easy to apply the method. And the method is not the particular cut elimination for Gregorchik, for GRC. It's in.
I see.
It's in general to improve translations.
In other cases, we cannot just we can just refer to your work and say, okay, then we have cut elimination according to these methods, and that's it. Now.
Yeah. Hopefully, if we arrive in time to the cut elimination part of the talk, I will explain what is the general idea, and it's what you have to prove once you have all the machinery. It's really short, in some sense, or is, yeah, I will say short, and obviously there is another detail, which this coalgebra is used to describe the method. The method uses a co-recursion, but obviously there are other ways of describing co-recursion. So maybe you can get shorter technical details if you use, I don't know, maybe you can use domain theory or other approach to co-recursion to be able, but that we have not done that because honestly what we wanted is to get this uniform method and then apply it to some examples.
Interestingly, it's interesting, and whether if we would try to state this general result via ultrametric space in the same.
That possibly can be another way of doing it. Probably you can also use ultra, because at the end it's here. This is the main idea. This is the main intuitive idea. This is all we are doing, and it doesn't matter. So by this, by the way, I mean the slides that I'm showing now. And once you prove that you can do this kind of thing, you can do the cut elimination. And the idea is basically, so imagine you start with a non-well-founded proofs. So here the black triangles are non-well-founded and the blue ones are finite. So the idea is you have an alpha, which we call it a step or a proof translation step. And basically a step, the only thing that does is given a non-well-founded proofs, it gives you a finite proof, and then to some of the leaves of the non-well-founded proof, of the finite proof, some of the leaves are connected to non-well-founded proofs. This is the step. And now what you do is, okay, I have a non-well-founded proof. I apply this alpha. I obtain a finite proof, and I obtain that it is connected to some non-well-founded proofs. So I put those non-well-founded proofs on top, and I apply the co-recursion again. Now, once I have done this, well, we can see how this evolves, and it will evolve given some finite proofs, or finite fragments, sorry, to be more precise, some finite fragments, and on top, some non-well-founded proofs, which you still have to apply the co-recursion. If you go through this to the infinite, at the end, what you obtain is this, which is a finite fragment, and on top of it, some finite fragments, and on top of it, some finite fragments. The idea of why this is preserving the branch condition is because we are ensuring that whenever you change from one fragment to other, it must be because you are progressing. So basically, a fragment ends. So one fragment ends and another starts exactly where there is progress. So you know that if you replace one fragment for another, which in essence is what is happening, it's a little bit more general than that, but you can see it in that way. If you replace one fragment for another, you are sure that you are not losing progress. That's the whole idea. This is the main idea. And now, this process, we describe it via coalgebra, but it probably can be described also via finite approximations using domain theory, because if you think about it, what this is saying is that this is a finite approximation of the final proof, and then this is a closer finite approximation of the final proof. And probably this part can also be developed using ultrametric spaces, because at the end, the only thing we are doing is a co-recursion. So if you can describe co-recursion in different ways, then you can define this part in different ways. I also hope yes?
Maybe the point is what approach is more concise.
Yeah. Like, yeah, it would be good to see which is the more concise. We can try to look at it, but yeah, there is no, in that sense, there is no, how do you say? There is no importance that the methods are coalgebras or ultrametric or finite approximations. The important thing is this idea of, which, as I said, is a little bit more general, because this can be generalized a little bit more. But this idea of, okay, since I'm changing a finite fragment for other, I know that I'm not losing progress. And this is also why you need that the system is local progress, because in other systems, this is not so easy. We have some ideas of how try to do it, but it becomes harder. So let me see the time. So we have 40 minutes left, right?
Yes, we have 40 minutes for the rest of the talk.
So I think, I believe this intuitive idea is clear. So I think I'm going to skip all the Coalgebraic details. Basically, here there are the exact definitions of that we use to define this co-recursion process that changes some finite tree of a non-well-founded tree for another one and continues. But I think the intuitive idea is much more important than the exact details. And now I will say that this part is important. So this is basically where we are going to define some conditions. So just to remind, we have basically what we have to do is define this step. So defining that given something that given a non-well-founded proof gives you a finite fragment, and then some non-well-founded proofs which are attached to some leaves of it. Once you define this alpha, this exclamation alpha follows by co-recursion, is uniquely defined. Now, what we are going to do now is put some conditions over this alpha, which in general is defined for non-well-founded trees, not only for proofs, but we are going to put some conditions into it such that we know if we start here with a proof, we end here with a proof. That is the whole point of this section. Because as said, the co-recursion in general gives you a tree from a non-well-founded tree or a finite fragmented tree from a non-well-founded tree, or from another finite fragmented tree, better said. Sorry, yeah. The co-recursion, to be more exact, gives you a finite fragmented tree from a finite fragmented tree. But we want that it gives you a proof from a proof. So in order to do that, we need to take these finite fragmented trees, which are just the trees seen as some finite tree and some finite trees on top and some finite trees on top and so on. And we need to say when these trees are a proof. The idea is that we are going to look at these fragments. So let me skip the definition. I think it's better to look at the intuition again. So the idea is that you can take any of these fragments and then you can see if it is generated by the rules, which is a first condition that we will want. So we impose that any fragment is generated by the rules. We also want, as we said, that whenever you exit the fragment, you are making progress. So basically, this means that if you have a leaf that is connected to a non-well-founded proof, then when you go from the conclusion to the premise, you must be making progress. And also for bookkeeping, we also make it the other way around. So we also impose that if the fragment ends in something that is connected to a non-well-founded proof, then it must be because it makes progress. And it's the only case. So notice that these fragments in particular have two kinds of leaves. They have the leaves which are axiomatic, and they have the leaves which we call them non-well-founded because they may be connected or they are connected to a non-well-founded tree on top. Now, well, basically this is another detail that we are not going to see because we are not looking at the definitions, but the idea is that these fragments in principle don't have a sequence associated to the non-well-founded leaves. So in order to claim if a fragment is a proof fragment, you need a fragment and you also need an association of these leaves to sequence. This is what is displayed here graphically. But again, this is just technicalities of the particular representation that we put. So then with this condition, which again are just a fragment must be generated by the rules, if there is progress, it must end. And that's the only case where it must end. Obviously, it must end in the sense of being connected to something else. It can still end in an axiom, and that's not a problem. So basically, once we have those conditions, we have what is a proof fragment. And then a finite fragmented tree is a proof if any of the fragments is a proof fragment. And here, again, you need to associate some sequence to the non-well-founded leaves. And basically, it's really clear, no? So if you have this shape, what are you going to associate to this non-well-founded leaf? Well, the conclusion of the thing that was on top of it. That is what makes sense. So that's basically, now we have two kinds of proofs. We have the non-well-founded proofs, which are a non-well-founded tree with some condition on the branches. And we have the finite fragmented proofs, which are finite fragmented trees and whose condition for being a proof is just that any fragment is a proof fragment. This is a really easy lemma. So basically, you can go from one to the other. So if you have a non-well-founded proof, you can use this relation that we defined at the start of the talk to get a finite fragmented proof. And if you have a finite fragmented proof, you can omit the equivalence relation or partition to obtain a non-well-founded proof. So this basically means that we are not doing anything crazy by redefining proofs in this setting. We only have what are the original proofs. And now here, this is probably the most important definition. We are going to define what is a proof translation step. Again, a proof translation step is going to be, in practice, an alpha, such that when you extend it by co-recursion, you know that you go from proofs in a non-well-founded local progress system to proofs in another, or maybe the same, local progress system. So here is the definition. Basically, it says the following. Imagine you have two local progress systems, and you have this alpha, which, okay, here there is the notation, but the idea is that it takes, yeah, you can see it here. The idea is, again, that it takes a finite fragmented proof. Notice that at the start, these were non-well-founded, but now they are finite fragmented because in proofs, we know how to go from one to the other and vice versa. So we can treat them equally. So you start with a finite fragmented proof in C0. So again, so everybody understand, you must think about this object as this. And basically, once you apply alpha to it, it must return two things, no? Well, in principle, what is finite tree and some non-well-founded trees. Again, in this particular case, since we are with proofs, we can think about this as finite fragmented. And the point is that this finite tree must be a proof fragment in the system we want to end. And these finite fragmented proofs must be proofs in the system we started. Is that clear? Or like, I will explain why this is like that now, but it is clear what I mean here?
Two non-well-founded leaves at the same time belong to different systems, maybe in different countries.
So that the non-well-founded leaves, so it's really easy. Basically, you have a fragment. No, a fragment is a finite tree. Now it's going to have leaves. The leaves may end in an axiom, and that's great. Those are great. But it may also end, if you think about it, it may also end in an open assumption. That's the idea. This open assumption is a non-well-founded leaf because if you leave an assumption open, you are in the compromise of putting on top of it a proof that proves that assumption. That's the idea behind. By technicalities of the Coalgebraic approach, this non-well-founded leaf is not going to have a sequent. But this is a technicality. So what you do is you assign the sequence that makes sense, which is just the sequence that when you see the proof is in there, when you see the whole proof, not only the fragment.
Yes, I see, but I just try to imagine the general case where this sequence in this non-founded node.
No, like the proof on top is not necessarily infinite, if that's what you mean. But here we use non-well-founded as possibly finite, possibly non-well-founded proofs.
Yes, I understand it. Just I try to imagine the case, the general case that there are two probably non-well-founded systems, and this recursion step transforms a proof of the first system into a small fragment, finite fragment, and possibly non-well-founded proof of the second system. And these non-well-founded leaves of the fragment, they somehow must fit into the first.
Okay, I think I know where you are going, so let me explain. Basically, there is a detail which is here, and it was the next thing to explain. So in principle, when you apply the alpha, the conclusion of this doesn't need to fit into here. So it doesn't need to be the sequence that you need. Because if think about it, if alpha changed the conclusion sequence, when you apply alpha to this,
yes.
the conclusion sequence will change here. And that is what you need to fit. It's written here. So what you need is that when you apply alpha to this and you obtain a conclusion sequence, that conclusion sequence must fit. This is what is written here, and it's also built into the definition, which is this. So this is the assignment of sequence to the non-well-founded leaves. And basically, this finite tree is the one that you obtain if you apply alpha to the non-well-founded tree. Of course, this only happens if your alpha changes conclusion sequence. In cat elimination, this is not going to arise because you have the same conclusion sequence every time. It's now clear?
Yes, so this is one of conditions which we require conditions of this step, co-recursion step, co-recursion proof translation step.
Yeah, the proof translation step. Yeah. This is one of the conditions. Yeah. Was there any additional question? Because I'm not sure I hear well.
Just I try to capture it a little bit better and to recall that there must be such a condition as kind of fit, kind of harmony between two calculus in a way that this co-recursion step must accurately translate the roots of proofs of the first system.
Yeah. And if you think about it, this is really similar to what happens when you do a co-recursion, that instead of doing it on finite trees, you do it only on the conclusion node. It has a similar behavior in that case. But maybe that's another topic. Okay, so here I wanted to make additional observation, which is here we are focusing in going from proofs to proofs, but this is in fact more general. In general, what you can have is a set X, like this, and then what you need to ensure is that whenever you start in something of X, so if you start in something here of the set X, then these things are still in X, and now this is a proof fragment of C1, and it is a proof fragment again in the sense that you need to apply alpha here again and see what is the conclusion that you get of the finite tree and put it here. But this is much more general, and this can be, for example, useful if you have a co-recursion that wants to act in a way until it finds something, and then it want to change its behavior. So for that, you can take this set to be proofs times 0, 1. And then the 0 will indicate one kind of behavior, and the 1 will indicate the other kind. And you may change between those. So just to mention that this can be useful, and it's more general. You can even start with something that has nothing to do with a proof, but we have not found a useful case for this yet. And well, this is the main theorem. So basically, the main theorem is what I have said out loud quite a lot of times by now, and which is just if you start with a proof in C0, you end with a proof in C1. If you have defined this exclamation alpha, where alpha is a proof translation step. Here there are two two statements, because one is for finite fragmented proofs and the other is for non-well-founded proofs, but essentially they are proving the same. The two is just a easy corollary of one, and this lemma that says that you can go from one kind of proof to the other and vice versa. And this is the method. So as you can see, in general, it can go from proofs to proofs, and this doesn't necessarily need to be a cut elimination. But now we are going to see its main application right now, which is cut elimination. So basically, we assume we have a cut rule, which is it's the usual cut rule where the context is shared is the same in both premises. And now we consider this system, which is just the original system we had, but adding the cut rule, and local progress only occurs when it used to occur. So just occurs in the right premise of the modal rule, of the box rule. Here, there is something I want to notice. So the cut elimination was already proven by Sabatif and Shankanov via ultrametric spaces. We have already talked about it. This was also used, which I think it's important to remark, to obtain a Lindon interpolation property proof theoretically, because the proof until that moment was semantical, and with this, they obtain a proof theoretical proof. But yeah, so basically the main difference between the method is that here you use ultrametric spaces, and now we are using just a co-recursion, capturing, adding these fragments, putting this fragment when they are right to be. Now, what they want to claim is that this cut elimination method highly resembles finite cut elimination, which I believe is a good property. For that, just let me say how cut elimination works in the finitary case in the big picture. So basically, the idea is that you have a finite proof and you have some cuts on top of it. And now what you do is, okay, I want to eliminate a topmost cut that doesn't cut. So basically, a cut that doesn't have any cuts on top of it. In order to do this, you usually put some measure to these cuts. And basically, you can show that you can eliminate such a topmost cut by some argument using some transformation that don't increase. And in particular, they strictly decrease the measure. In particular, one of the measures that is usually used is the sum of the height of the subtrees that you get if you go to the premises of the cut. So this is quite the standard. Now, once you know how to eliminate a topmost cut, the thing that you do is an induction argument. You assume, okay, if my proof has no cuts, I'm done. If it has n+1 cuts, I go to a topmost cut, I eliminate it, I have a proof with n cuts. By induction, I can eliminate it. So this is the finite induction argument. You can see here, there are the three steps. So finding a measure, showing that you can eliminate topmost cut, and showing that then you can eliminate all cuts. Now, well, and in particular, notice that in general, what you want to do is 1 and 2, because once you have 1 and 2, once you know how to eliminate topmost cut, you know how to eliminate all cuts. This is, in some sense, going from 2 to 3 is quite uniform. What is going to happen now is that we have 4 steps, but again, once you have done 1 and 2, going from 2 to 3 and from 3 to 4 is quite uniform. So we are going to have something that is really similar. And now the idea is that we have to find a measure again for the cuts. And this measure is also usually going to involve height, but now we cannot talk about height because we're in infinite proofs. But since these proofs are fragmented into finite proofs, if you have a node here, you can talk about its local height, which is just the height inside this finite fragment. So we are going to use that measure, the local height, instead of, so the local height of the premises of the cut. Now, once we have that measure that usually involves this local height and other things like the rank of the cat and things like that, you can show by induction in the measure that you can eliminate a topmost cat. So this is completely, well, sorry, you can eliminate a topmost cat is not the exact correct words. The exact correct words is that if you have a proof which only have one cat at the bottom in the main fragment, so basically, let me zoom here. So imagine you have such a proof. Oops. Imagine you have such a proof and you have only a cat in the main fragment. There is only one cat, which is at the root. And then there may be more cats on other fragments. In the other fragment, there may be arbitrarily many cats. What you want to show is that you can eliminate this cat there. And the idea is that while you eliminate it, it may be the case that you increase the number of cats in fragments on top of it. But this is not going to be a problem. But the idea is that now we are not eliminating the cat, we are pushing it upwards. We are pushing outside the bottommost fragment. That's the idea. Is that more or less clear what I mean?
Yes, it's understandable, completely understandable.
Okay.
I don't know how about other participants, but I hope
About what?
other participants.
Yeah.
Hope it is clear.
Well, if I don't receive any complaint, I believe I should continue.
Yes, so it is a general idea to move cats bottom up and somehow try to find some basis why why we obtain a non-wellfounded proof during the process.
Yeah. In particular for traces, we are trying to generalize this for traces, not only local progress. And the ideas are similar. They are different in many respects, but the ideas are similar. The ideas are you have a fragment that in this case may be infinite, and you want to push the cats outside the fragment to be safe. So this is basically the main idea of cat elimination using these fragments. But well, in principle, we have only talked about how to eliminate one cat in the main fragment, a topmost cat. Now, let me explain the other two steps, otherwise this is incomplete. So you basically going from 2 to 3 is exactly going from 2 to 3 in the finitary case. The idea is, again, you do induction in the number of cats in the bottommost fragment, which, by the way, from now on, I'm going to call main fragment. So you do induction in the number of cats in the main fragment. You pick a topmost one, which is topmost in the main fragment again. So you may have cats on top of it, but not inside the main fragment. And you eliminate it, or you push it upwards, and you do that for all the cats. So it's completely analogous. And then what you have obtained is a step that starts with a proof that has some cats in its main fragment and ends in a proof with no cats in its main fragment. You can see this as a proof translation step. And basically the idea is that you return this fragment free of cat as the finite tree and the proofs on top as the non-well-founded trees. And here it is essential, it is really important that if you notice in our conditions, these things are proofs in the original system. In particular, they are allowed to have cats. That's not a problem. That's totally not a problem. So it's fundamental to have that. So this is the idea. And now we use this idea to show cut elimination for this logic I was talking at the start. And basically here you need to define, because while you are eliminating a topmost cut in the main fragment, it may happen that you ruin things. Like, for example, if we're eliminating a cut, you introduce another one that is not eliminated, that's a problem because you are left with another cut. Or if you start increasing the local height of the main fragment while you are trying to eliminate it, it may be the case that you increase that local height too much and you never stop. So you need two conditions, basically. You need, basically, when you have a function from non-well-founded proofs to non-well-founded proofs, you say that it preserves local height if the local height of the application of the function is smaller or equal than the local height of pi. And here with the local height of a proof, it's obviously the height of its main fragment. So this, in some sense, it's going to guarantee that so we want to reduce, we said that our measure has as part of it the local height. We want to be sure that we don't increase it. And this is the way. Basically here we are saying we are not increasing. This is the condition saying we are not increasing the local height. And the other is preserving freeness of cut, which basically a function preserves freeness of cuts in the main fragment if whenever you start with a proof that has no cuts in its main fragment, then, and you apply it to the proof, the function, you obtain a proof with no cuts in the main fragment. The important thing is that the usual the usual functions that you use in the argument of eliminating cuts, like inversion, like weakening, like contraction, all of those fulfill these two conditions. And a really good thing is that these two conditions really seems really natural to ask. But yeah, basically the idea is that these rules, these functions that we use during the cut elimination fulfill these conditions. By the way, I want to remark something here. Basically, here we are claiming that a modal rule is invertible. And this is not something really common, but if you look at the system, you can see that, well, it is, no, the system was much later, sorry. Basically, this is just a detail, but I want to mention it. I'm not finding the, oh, it's here. It's here, yeah. So basically, the idea is that from here to here, it is invertible, but from here to here, it is not, because you are losing all these formulas in this way, but here you are keeping everything. I just wanted to mention, because when I was preparing the talk again, I was surprised that we were using, like I use it, I forgot that I use it, and then when I was reading, I was saying, how a modal rule being invertible? This looks really strange. And well, it's because here you are keeping everything. It's important to remember. But yeah, so once you have this lemma that all these functions have these good properties, you can do, as I said, you can show that if you have two proofs that have no instances of cut in their main fragments, and then you can obtain a proof of the cut without instances of cut in its main fragment. And then you can use this by defining this function, which basically you input it a proof and it returns a proof of the same sequence with no cuts in the main fragment. And then using the co-recursion, you get the cut elimination. So I'm not so sure how time we have left. Not that much. But maybe I can finish the talk, and then if someone wants that I show, for example, how you push the topmost cut, I have basically the argument after the end of these slides, or I have part of the argument so we can recreate it. But yeah, the main idea is that you can do all this process. And the good thing is that, in fact, if you change the system, so for example, we also use this method to prove cut elimination for weak GRC. which was also shown that has cut elimination by Sabatif and Shankanov. And you can also use this method. And the good thing is that you only need to do 1 and 2. 3 and 4 are straightforward once you have 2. But yeah, let me say some conclusions. So, well, as I said, one difference with the method by Sabatif and Shankanov was that they use ultramatic spaces and a fixed point theorem. And now we do not take this detour through ultramatic spaces, but it can be argued that we take a little detour through coalgebras. But in general, this detour is taken because we need a rigorous way of defining co-recursion. That's the only thing why you need it. And as I said, the method can be used straightforwardly to show cut elimination for the weak version of the system, for the weak GRC. And as I exposed in the previous slides, this method highly resembles cut elimination for finitary systems. Now, about future work. Well, there are various lines of work here. The most obvious one is that, as I said, this method works for the easiest kind of non-well-founded system that there is, the local progress. So a natural route will be, can we do this in harder systems like trace systems, which nowadays are really popular because you can express, you can have proof systems for modal logics with fixed point using these trace systems, for example. In particular, right now, we are trying to work out this, but for the master modality, so K+, which is also a trace system. A second thing that can be interesting is finding another applications of this method, because as I said, cut elimination is just an application of the method, but the method in general allows you to generate proofs. In fact, you don't, as I said, you don't even need to start with a proof. You may start with something different even. So it would be nice if we can find another interesting applications of the method. I have to mention that Lucas have found that in one other work he was doing at the same time as this, he found himself that he was using this without noticing, when in particular, when in a transformation, in a translation from an intuitionistic multi-conclusion segment calculate to a single conclusion one. Basically, this idea of going to the end of the main fragment and do something there, and that idea also appeared there without noticing. So there may be another interesting applications for this. And the last future work that we are considering. So basically, we presented this work for advances in modal logic, and the reviewers asked us a question that we also had, but we didn't have the time, or maybe we didn't have the intelligence to solve, which is what is the exact relation between this method and continuous cut elimination. So cut elimination using ultrametric spaces. Because, for example, for the master modality, the one that we are exploring right now, Shankanov already showed cut elimination using ultrametric spaces. So can we adapt this method so we can also do it? Or maybe this method is intrinsically weaker? In general, the agreement is that for sure, cut elimination with ultrametric spaces is no weaker than this one. So the only possibility is that this one is weaker. That's the intuition the reviewers and me personally have. And what? Here there is some bibliography. And I think, unless, well, yeah, I will leave it here. So feel free to ask any questions if you want to. Thank you for your attention.
Thank you for your talk. I have some questions, and maybe I would stress that the third point of the future work seems very interesting for me at the first one, but maybe some other participants have remarks, questions, comments.
Well, I have a comment. For pure derivability in logics of Gödel-Loeb or Gregorczyk type, there is also this thing called circular or cycle proofs, that these proofs can be wrapped up in a finite structure. So how is this reflected by this, say, Coalgebraic approach? Is there some making things easier or something like that?
Yeah. That's a really good question. Thanks a lot. That reminds me that here I forgot to put an extra point, which was a question by the reviewers that we still had not the time to answer, which is if this method of cut elimination preserves regular proofs, so cyclic proofs. So that's still a question we don't know to answer. The reviewer was expecting that it does, but I'm not so sure. So in principle, if you think about it, in some sense, it makes sense that it preserves regularity of proofs, but at the same time, when you start, as I said, I have not started to work formally of this, but when I was thinking a little bit more about it, imagine you have a regular proof and you have the main fragment, and the main fragment is repeated some point on top. While you're eliminating the cuts here, you are pushing them upwards. So in principle, it may happen that while pushing them upwards, you add some extra cuts to the repetition of the main fragment that was on top. So obviously, it may be the case that you can show some property that in a regular proof, before that repetition, you have eliminated the cuts, not push them, but eliminate them. But I don't have a tendency to believe any of the two yet. Probably my idea is that it will really depend on how you are pushing the cuts outside the main fragment. And obviously, just to remark, in general, obviously, but I assume this was not part of the question, but just to remark for people which are not in non-well-founded and cyclic proof theory, obviously having a method for cut elimination in non-well-founded proof theory is in some sense more powerful than for cyclic, because any cyclic can be seen as non-well-founded, but not vice versa. That is just for people who are not into the area. But yeah, the question of preserving regularity, for example, is still open.
So do you pose it in this very strong sense that your procedure will preserve regularity?
No. I say I'm agnostic about it until I really think. I think, and again, it will depend on exactly how you push the cuts outside the main fragment. I think it will highly depend on that.
No, because usually you need something weaker, that you eliminate the cut, you get some proof, which is irregular probably, and then you just prove that this is you can transform it into a regular proof after cut.
Yeah.
But why I was interested in the procedure itself, because there are some cases when regular proofs are are incomplete. And so the logics are different. And in this case, procedures which will, so if we take a regular proof, which is circular proof, and then perform cut elimination, then you will get something, and tracking its properties, it could not be circular, but regular in some sense, would give you some new cut elimination or cut normalization results, which could be interesting. For example, what I'm doing in infinite reaction logic, where it's a different thing. You cannot say that you can just regularize anything. It's just false. Different complexity.
I see. No, we are really interested in the question. The problem is the review was not like we received the review like 1 week ago, and we didn't have the time yet because we are also a lot focused in trying to generalize for the master modality, but we are also interested in that question and we want to solve it. As I said, it all depends probably if you can guarantee that you can in some sense not push the cuts but totally eliminate them, because some repetition of some iteration of the repetition appears, which I'm not sure. I think it will really depend on the logic and on how you push the cuts.
Okay. Okay.
Although I have to say that the reviewer was confident that, or he was suggesting that it may be the case. But I'm still agnostic.
Let me add maybe several thoughts. It seems that in general, this procedure shall not preserve regularity. And there is an intuition, so to say, in the air, not only mine intuition, that maybe we shall consider some automata generated trees, not only generated by ordinary finite memoryless automata, cyclic proofs, regular proofs. They're generated just by finite automata without any memory, just finite number of states. And there are many generalizations of this notion, such as push-down hierarchy of automata generated different classes of more and more complex trees, and maybe we shall consider this question in this from this perspective. If there are non-wellfounded trees generated by this kind of automata, this hierarchy, then this procedure preserves this class of hierarchy, or maybe increase the complexity class of the trees, something like that. But it's unclear at this moment.
Yeah.
You know.
I would be really happy if you can give me references to these uses of proof, of automatas for this cut elimination in non-well-founded proofs. Because I want to explore it in that way, but I'm not familiar with the area.
I met several, so to say, questions or hypotheses in different places, like something Canal in his semantics of cyclic proof, or this paper, I don't remember precisely the title. And Bahara also told me that she thought about this in this direction, and I also met this intuition in conversation personal, but I don't know at this moment some papers where this idea was elaborated.
Well, we can discuss it later, but it's good to know that you have some ideas around that.
Yes. So, but this idea, so to say, in the 10 years or more, but up to now there are no achievements, no progress in this direction. Fyodor Pakhomov also told recently about the same idea, but similarly, some work shall be done in order to somehow unfold this path, unlock this path or this door. Okay, dear participants.
It would be also interesting to do something for the predicate logic that you proved completeness theorem, Daniel, for topological semantics with respect to these systems. Logic.
Yes, Valentin Borisovich mentions a result of Pavel and mine, where we prove, where we consider the Gödel logic with quantifiers, first order quantifiers.
Yes.
Non-well-founded derivations, non-well-founded proofs, and show that this infinite system is complete with respect to topological semantics whereas the finite ordinary quantified Euler logic is not complete.
Yes.
And it seems that the same line or the same intuition works also for in that case, but I'm not sure exactly whether they
Well, cut elimination may exist still. Yes.
cut elimination holds, yes, but
Yes.
the question is whether the
Sorry.
whether the apparatus of Borja already captures this case or not.
Related to the first order logic, I have to say that we have in a scope a system that, as far as we, basically we have a system of true arithmetic, which we achieve to give a local progress calculi. Basically, the idea is that you really need a trace, but if you control how many times you use a particular rule, you can become it local progress, and the way of controlling that is adding ordinals to the sequence and ensuring that whenever you apply the rule that you don't want to apply too much, you lower the ordinal. Basically, using that idea, we have a local progress system for true arithmetic, and we are trying, well, it's in our to-do work to see if we can use this method for proving cut elimination there. But as I said, we are with the master modality right now.
Yeah. Yes.
And in principle, so we have not checked the idea, but the intuition is that we will have to do this. So basically, there are some cuts which are harder to eliminate. And the idea is that you do this process to eliminate all the cuts except this one that are harder. Then you do one step, eliminate or converting these cuts into the others, and then you repeat. And this may go on and on. So it will be interesting because it's different. It's not exactly as here. It looks like, at least, but we have to check in detail.
Well, it's partially the same, right? It's we can use our method to eliminate all the cuts apart from some difficult cuts, which then can be reduced in the limits, and then the whole method can be iterated. So if we assume that there is some global cut rank in proofs, we can do some recursive argument to get rid of them. At least that's the hope.
Yeah.
Maybe a question. Just I wonder whether your notion of local progress sequence calculus, whether it captures also a quantified system.
Which quantified? So
you have a general notion of a local progress sequence system.
Yeah.
And I wonder whether this notion also generalizes or captures quantified sequence systems. For example, just ordinary finite sequence calculus for classical logic.
Yeah, I think it has. So in principle, a sequence in this setting is an abstract thing, totally abstract thing. It doesn't even need to be two-sided or something like that. Basically, the importance of is the local progress, is how you define the condition to restrict possible infinite branches. That's the important part.
So the condition on variables, on bounded variables, are somehow already captured in your notion of an instance of a rule. Or...
Yeah, I will think so. I think, in fact, I believe the notion of rule instance I put here is not new. I think I have seen it elsewhere, like, or at least an abstract definition of the second calculus without the local progress part. without that L. So that L is the important part, in fact. And what we have noticed recently is that the local progress is more than we initially expected, because in principle, we expected local progress to be, well, it's more than you expected if you allow ordinals, let's say. Because in principle, we only expected things like these modal logics, but then we noticed that there are many other systems, like, for example, the master modality system that you propose, which can be expressed. So the condition on the branches is something like there is something that must happen infinitely often, and there must be other things that never happens. Now, so basically you have a suffix where you have something going infinitely often. You have a suffix of the branch when something happens infinitely often and other things cannot happen in the suffix. We notice that you can go from that kind of system to a local progress one if you add ordinals to your sequence. So you annotate every sequence with an ordinal, and whenever you apply one of these rules that you don't want to apply infinitely often, sorry, that you don't want to apply at all in the suffix, you reduce the ordinal. And then it's a local progress again. And the problem with this is that it doesn't necessarily mean, so you have local progress, that's true, but still the cut elimination it can be much harder. The cut elimination doesn't need to be as natural as for, let's say, true local progress systems.
I see that at this moment there are, so to say, a variety of attempts to tackle this more complex calculus, and this labeling with ordinals is one, or adding some annotations is a way to reduce the local progress system.
Yeah. The problem is that, for example, if you do this for the master modality, is you cannot replicate the cut elimination here. So you cannot do push the cuts outside the main fragment and you are done, because you also have traces and these also interact with the traces. So we believe that you can still doing it, fragmenting the proof, but now you may get infinite fragments and things like that.
I see that there are some technicalities and we can tackle this, but before it, I just say, could you maybe could you show me your calculus that you mentioned about arithmetic and local progress system for true arithmetic, maybe later?
Yeah, later I can show it. I may need to find the tech file, but that's all.
Okay. Other questions, remarks, comments?
Yes, let's thank the speaker. What we did not do.
Just a personal comment. I hope to meet you in Bern and Warlick, where I'm going.
Nice. Yeah, that's
maybe
nice.
have a bit more discussion then.
Yeah, perfect. I would love to.
Thank you for your very interesting talk.
Thank you very much.
No, thank you for your attention.
Okay.
Borja